Welcome to our member seminar. And our speaker today is Ruixiang Zhang, and he will talk about the nonabelian Brunn-Minkowski inequality. Please.
All right. Thank you so much for the introduction, and thanks a lot for having me. And hoping all best for everyone for the new semester. Okay, so today I'm going to talk about the result that's jointly with Ruixiang Zhang at UIUC and Min Chuan at Notre Dame. I believe both of them are in the audience, so very good. And if you have any questions, just feel free to ask anytime. Okay, so I'll be using slides, and let me know if you cannot hear me well for any reason. So assuming it's going on well now. Okay, so today I'm going to talk about the Brunn-Minkowski inequality and actually a non-abelian version of it. So here's my plan, and I'm going to first recall what the Brunn-Minkowski inequality is. It's very elementary, at least as stated in Rn, and then talking about a natural question about generalizations of the inequality for locally compact groups. And then, I mean, it will be too difficult to present the whole proof, but hopefully I can present important ideas in the proof for an important example. That's the case when the group is equal to SL2 of R. And then maybe if I have more time, I'll say a little bit about what we need to do for general topological groups. As we'll be seeing that, I mean, a priori, this is a question for topological groups, but for locally compact topological groups, but it's really much about Lie groups. So you'll be seeing this in a bit. But before that, let's just recall what's Brunn-Minkowski inequality. And I mean, it came from this place where you can ask a natural question about measure of some sets on any Euclidean space. So on an Euclidean space RD, you have a standard Lebesgue measure that's called mu or d mu. And then you can study some sets because you have an operation that's addition. So for non-empty sets x and y, I require them to be compact so that the sum will be compact and measurable and everything. And then you can define the sum set x plus y to be the set of little x plus little y for little x in capital X and little y in capital Y. And then you have this very simple question. If you're given mu of x and mu of y, if you know the big measure of x and y, then how small can this mu of x plus y be? And people have studied this question very well. And one very useful conclusion along these lines is the Brunn-Minkowski inequality. So I showed in this slide. So assuming you have x and y in Rd, then if you raise mu of x plus y to the 1 over d's power, it's going to be at least mu of x to the 1 over d's power plus mu of y to the 1 over d's power. So I give you a very explicit example here with random numbers, but shows that this is a very sharp inequality in R2, and the same way in any dimensions. So here our x and y and x plus y are parallelograms that are similar to each other, and you just compute their measures, say they're 25 and 9, and then you know that x plus y has measured 64. So you realize that if you raise everything to the 1/2 power, then you have this equality. And in fact, you have this inequality in general, and that's known as the Brunn-Minkowski inequality. I believe I still have it in the next page. Let's see. Yes. So a little bit about the history. So Brunn actually proved this for convex sets, but in another form. And then Minkowski actually gave a proof again in the convex sets. But more importantly, he brought up this form, which ended up being very useful in other contexts. And also he studied a little bit about, I should say very well about when you have the equality for convex sets setting. So that's all his. And then later on, Lusternik was able to prove this inequality for arbitrary sets with a little bit of caveat, like there are some measurability issues, but he has the essentially correct proof of the currently stated theorem. And then the most rigorous proof and more I think more discussion on the equality was given by Henstock and McBeast, so in 1953. So I think it's fair to say that it's a theorem of all of them. And one thing that we just noticed is that the exponent 1 over d is going to be sharp. So what do I mean by sharp here? If you think a little bit about it, you know that this inequality gets stronger if you replace 1 over d by smaller numbers and gets weaker if you replace it by bigger numbers. So mu of x plus y is always going to be bigger than mu of x and mu of y, just by translation invariance. Being sharp just means it's the smallest possible, and actually you can have this smallest possible value attained. And sometimes this inequality takes some more familiar form in a very important special case where you have mu of x equals to mu of y. So those two have the same measure. Sometimes you even consider this inequality for x equals to y. And then in this context, you would have this inequality read as mu of x plus y bigger than or equal to 2 to the d times mu of x. So that's a more familiar form of this inequality. And you see 2 to the d comes out naturally if you take x and y being the same, for example, parallelotyped, and then you have this equality. Okay, so this is the Brunn-Minkowski inequality, and we're going to ask a question that generalizes it. So how to generalize this inequality to other spaces? Well, you first need you need an operation between elements in the space. So the most natural setting is that you require the whole space to be a group where you have a group operation, you have a multiplication. And then you also want to have a measure that's very canonical. So we're talking about additive stuff. So your measure better be translation invariant in some way. The most nice setup would be in the so-called unimodular locally compact groups. So I'll explain what that means. Okay, so recalling a little bit about the terminology, I just said if you want to generalize this question, you better ask it on a group. At least that's a natural way of asking it. So you can ask it for a topological group. We require it to be locally compact so that it has a very nice measure. So every topological group has a continuous group operation. Actually, the inverse is also continuous, and you can define. So the conversion here should be x times y to be in the same way. You take little x in capital X and little y in capital Y and take the set of all little x times little y. And actually, if you require the group to be locally compact, you have a very nice theorem by Haar saying that up to multiplication by scalars, there's a unique Borel measure that's left invariant, and we call it the left Haar measure. And similarly, there's a right Haar measure. And the most simple setup will be when the two agree. So we call the group unimodular if the two actually agree up to, again, multiplication by a scalar. So if a left Haar measure is also a right Haar measure, we call this group a unimodular group. And then I will give a little some examples of unimodular groups in a minute. But I'll just say that in this setting, we'll fix such a measure. I'll call it mu, and it has a name. It's known as the Haar measure. So we're going to ask this question in this context. Again, so given mu of x and mu of y, how small can mu of xy be? And this question actually can be quite difficult, and we'll pick a start. That's whether you can generalize Brunn-Minkowski to this setting. Since it was useful in previous contexts, it might be interesting to look at this inequality. Okay, so some examples about groups and about locally compact groups and unimodular groups. So you have familiar examples. Rn, which is what we just discussed. I should put Rd to agree with my previous discussion. And also you have the group of integers z, you have the torus R quotient by z. You can also take multiple dimensional variant of them, Cn and Tn. And some more non-trivial examples would include, say, SL2 of R. And then a very interesting object, as we'll see, the universal covering of SL2 of R. which is another group that's different from SL2 of R. And also you can ask this question for other groups like SL2 of FQ or the p-adic group SL2 of QP. But as we'll be seeing that the Lie groups automatically will stand out in the study of Brunn-Minkowski. So we'll be talking about that in a bit. And also I want to bring up a non-example. If you look at the group that's orientational preserving affine transformations of the real line. So you take the transformation ax plus b when a is bigger than 0, that's a group. But this group is going to be non-unimodular. So meaning that a left-hand measure will not be a right-hand measure, and they will differ by different constants in different places. So we'll be seeing the role of this group in our discussion. So that's just a non-example showing that a natural group can be non-unimodular. Okay, so let's think about this inequality over these examples. And I have an easy remark. Okay, actually, let's actually recall a little bit of history of this question. So it's asked by Henstock and McBeath, I think at least implicitly in their paper. And also later, I think I left out McCruden and also Hoshowski and, oh yeah, McCruden is here. Hoshowski and McCruden and Tao, they asked similar questions. They asked, I should say, special cases of these questions or conjectures. So you can ask this question for unimodular group. So you assume G is unimodular and locally compact and mu is the Haar measure. And the question is to find the sharp exponent alpha such that for now empty compact sets x and y, you have mu of xy to the alpha's power bigger than mu of x to the alpha's power plus mu of y to the alpha's power. So that's our goal. And that's the target inequality we're facing. And a few easy remarks. You see that alpha equals to infinity will suffice because you just choose an arbitrary y. And then you have, so when alpha is equal to infinity, this is just saying that mu of xy is bigger than the maximum of mu of x and mu of y. And the proof is trivial. You just pick an arbitrary little y. And mu of xy is bigger than mu of capital X little y. This is equal to mu of x by invariance. So alpha equals to infinity suffices. Another comment is that if our group is compact, this question it's not very interesting in its own right. So this is a little different. If you were at my new postdoc talk last semester, then you know that we were studying a different problem than I'm talking now. So when G is compact, this question is not interesting because infinity is going to be the sharp exponent because you just take an example where x equals to y equals to G, and then you will see that mu of xy is equal to mu of x and equal to mu of y. So G is compact, this case is not interesting. And similarly, another non-interesting case would be when G has an open compact subgroup, and then you just answer this question trivially, that alpha is infinity and you cannot improve it. So for several groups we have just seen.
Actually, don't quite remember the details of your talk, but if G is compact or even a SL2FP, then of course there is the expansion question which you have to quantify, which is plenty interesting.
Yes, of course. Yeah, thanks for the remark. But I'm just saying
but
that
it's not just for all, you can't take all sets, of course, yeah. Right.
Yeah, I mean, so it's possible that the other question can be inspired by some ingredients in the study of the current question, but you need to formulate the other question more carefully. Even for Z, you have a theorem that says that if you have a set of n integers, then the sum set has to have cardinality at least 2n minus 1. But when n is equal to 1, you will get 1 plus 1, and then you have another 1 element in the sum set. So in the formulation of this question, it's not interesting, but it doesn't mean that there are no interesting additive phenomena in those groups. I'm just saying for this Brunn-Minkowski, it's trivial. For the groups I am saying, for example, for the groups of integers, for the torus, for SL2 of FQ or SL2 of QP, so automatically this question trivializes. So we're not going to talk about those groups because that will require more studies. But this question is not always trivial. For example, you've seen that in R to the D, this is a very non-trivial question. And I'll show you another example where this question is non-trivial. So you can take the group to be SL2 of R, and then this question is going to be non-trivial. And I just rewrote the question here. You take the Haar measure, this unimodular, to be mu, and then you try to find the sharp Brunn-Minkowski exponent, meaning that the exponent satisfying mu of xy to the alpha bigger than mu of x to the alpha plus mu of y to the alpha. Okay, so I recorded a very interesting phenomenon in the last line or 2 lines. So SL2 of R has topological dimension 3. So you might think, based on what you have for R3, you might think alpha should be 1/3. But actually, this is not the case. Actually, there's a very elementary example saying that you cannot improve beyond 1/2. So the sharp alpha might be 1/2. And actually, in our paper, we were able to prove that the sharp alpha is 1/2. But let's look at the example first. So this example exists because SL2 of R has a non-trivial compact subgroup of dimension 1. So you take this maximal compact to be K, to be equal to SO2 of R. And then your construction will simply to be, you take a small closed neighborhood of K. So I can only show this picture topologically. That's what's also in our paper here. So topologically, SL2 of R is an open torus that's filled in. And then you take a small neighborhood of K as shown in the picture. And when your small neighborhood is sufficiently small, you see that mu of x squared is very close to 4 times mu of x rather than 8 times mu of x. So this can be seen by constructing an invariant metric on G quotient by K. But G has dimension 3, but this example shows you that you cannot improve beyond 1/2. And that's also what we were able to prove. So these are just a few comments to start with. Mu of x squared raised to 1/2 is close to mu of x raised to 1/2 plus mu of x raised to 1/2. But this can fail if you try to replace 1/2 by anything smaller. And we were able to prove, so jointly with Ifan and Min, we were able to prove 1/2 is sharp. Okay, so a little bit about the general conjecture. So this is completely general. I'm going to talk about what's our general result and what's our general conjecture for now. So let's move away from SL2 for the moment and then go to the general setting.
Let me ask another question.
Yeah.
In general, where you say this question was raised in 1953, there was no answer suggested.
No, I mean, so when I think when in Henstock McBee's paper, so their primary purpose was to prove the Brunn-Minkowski inequality because they think the Leutheris proof
in RD.
Yeah, in RD. So they talked about topological groups, but I don't think they made a conjecture. Even in later, like in McCruden's paper, I don't think he made a conjecture. So please correct me if I'm wrong. But I don't think they made a conjecture. Later on, there are conjectures about specific cases. There were wrong conjectures, but we were not aware of like this conjecture I'm about to say, like in the previous literature.
Okay.
Yeah. Okay. So the general case is a general locally compact topological group, and let's focus on one specific type of those, namely the Lie groups. So what's a Lie group? Let's recall a Lie group is just a finite dimensional differentiable manifold. That's also a group where the group operations are smooth. And so you can talk, for example, about the dimension of the Lie group, and we'll be seeing that. So the Lie group has a Lie algebra because you can, for example, use the left translation to identify the tangent space of the identity with the tangent space of any other point. So that tangent space has an algebraic structure. It's known as the Lie algebra. So we'll be using that in the talk later. So for any Lie group G, also all the subgroups are Lie groups as well. all the, sorry, we're interested in their subgroups as Lie groups as well. So we can define the following quantity. We can define M of G to be the maximal dimension of the compact subgroups of G. So this is well defined. If G is connected, there's a result saying that all the maximal compacts are conjugate. So you can certainly find it. And when G is not connected, you just look at connected components. So this is well defined. And so this is our terminology in our paper. We define the non-compact dimension of G to be the dimension of G minus this M of G. So this is what we define, what we call the non-compact dimension. And our conjecture based on the previous example would ask whether the following is true. So as long as G is unimodular Lie group, and then mu is a hard measure, do you always have mu raised to 1 over ng bigger than mu of xy raised to 1 over ng bigger than mu of x raised to 1 over ng and mu of plus mu of y raised to 1 over ng's power? We conjecture this is true. We also conjecture the exponent 1 over ng is sharp. So these are about Lie groups. And what about general groups? So those you'll see that the problem for general groups, general locally compact groups, are closely related to that of Lie groups because of a very non-trivial theorem. So there's a theorem called the Gleason-Yamabe theorem. It actually is a solution to Hilbert's fifth problem. So by that theorem, you actually know that every locally compact group G has an open subgroup G prime, such that you can find a compact normal subgroup H in G prime, such that G prime quotient by H is a Lie group. So in this sense, this problem is not far from the problem on Lie groups, because it's just not difficult to see that the Brunn-Minkowski exponent of G and G prime, they're the same, because you're taking open subgroups, and the additive phenomenon. This question on G is the same as this question on open subgroups. So if you think about it, although it can be trivial, for example, if you look at the question on Z, why is it the same as the question on 1 point? Because you just have that 1 point example to be sharp. So it can be trivial, but I'm just saying the Brunn-Minkowski exponents of G and G prime are the same. And also that exponent for G prime and G prime quotient by H is going to be the same, because H is going to be compact. So quotient by compact normal subgroup wouldn't hurt in this question. And that's the intuition. So based on this, we in our paper, we define something inspired by the previous Lie group case. We define the non-compact Lie dimension N of G to be the non-compact dimension of G prime quotient by H. So G prime quotient by H is a Lie group. And we define N of G in this way for general G. And we also show that this is well defined. So it doesn't have to do with the G and G with the G prime and H that you choose. So this is well defined. And our conjecture is going to be that 1 over ng is going to be the sharp Brunn-Minkowski exponent, and it's actually a correct exponent. So that's our conjecture. And we were able to prove this conjecture in, I think, in many cases, but there are still unsolved cases. I'll be showing you what we proved in terms of this conjecture next. So yeah. So I'll put this conjecture simply as this, and at this point I can present our main theorem. So the first theorem, as you might guess, comes from the same line of analysis as the torus example, that says that this exponent 1 over ng, if it's correct, then it's going to be automatically sharp. So the sharpness is proved. And the second part of our theorem says that you just need to verify this conjecture for simple Lie groups. Then you'll know this conjecture. Actually, we prove you can imagine that we use Gleason-Yamabe to reduce it to Lie groups. Actually, we proved a little bit more, saying that even if this conjecture fails for some simple Lie group, if we know the sharp Brunn-Minkowski for every simple Lie group, we should know. I mean, this is in principle. I think I mean, I forgot if we rigorously proved it, but in principle, if we know the sharp Brunn-Minkowski for every simple Lie group, we should be able to answer the question in general. So that's the second part. And the third part is our result. So we prove that the conjecture is true if we replace 1 over ng by 1 over ng minus hg. So there's a funny thing, hg that's always positive or non-negative. That's always non-negative. It's 0 in a lot of cases. So we prove the conjecture for sometimes itself, sometimes for a weaker exponent. So in our paper, we call this hg the helix dimension. Well, I'll probably explain why we have this funny name in the next slide. But if hg is 0, then we actually prove this conjecture. This actually has a lot of meaningful cases. For example, we were able to prove this conjecture for all real linear algebraic groups. And there are a more general class of groups called Nash groups. We were able to prove the conjecture for that as well. So as a special example, we actually prove it for SL2 of R. And I'm going to show you some ingredients in the proof after presenting this kind of theorems, these theorems. So for now, I'm going to tell you what h of g is. So the rigorous definition of h of g for one slide. Okay, so if you have a Lie group, let's take its identity component. You have the Levy decomposition, decompose it into the semi-direct product of a solvable group and the semi-simple group. So a group is solvable in the usual sense, if it's solvable in the usual sense, but a Lie group is semi-simple if its Lie algebra is semi-simple, so just for the notation. And the helix dimension is going to be defined as the rank of the center in the semi-simple part. So there's a theorem saying that a semi-simple Lie group always has a center being discrete and finitely generated abelian group. So h of g is going to be the rank. To be more specific, if you take, so let me just take one example. If you take, or two examples, if you take SL2 of R, then this S is itself, and the rank of the center, I mean, it's 0, so H is going to be 0. But if you take the universal covering of SL2 of R, then the center is going to be the same as Z. So the rank of Z is going to be 1, and then H is going to be 1. So we can prove that we cannot prove the conjecture for SL2 for the universal covering of SL2 of R. So I'll be talking about this.
So that's connected with the fact that you can do it for the linear algebra, linear.
Oh yeah. For linear algebra groups, this bad situation doesn't happen. So
right.
Yeah. So yeah,
you really can't do it for SL2 tilde. It seems like
yeah, we weren't able to, but we hope one day we can prove it. So you'll be seeing the reason near the very end. So yeah.
What's H in that case? 1?
So H is 1. Yeah. So we are still able to prove the exponent 1/2, but not able to prove it proving 1/3. Yeah. So the second comment I wrote here is just telling you how to define the helix dimension in general. So we call it the helix dimension because the universal covering of SL2 or any group of with H not equal to 0 might look like a helix. So that's the simple reason why we call it. So for general G, you use Gleason-Yamabe to go to a Lie group, and you define the helix dimension to be the helix dimension of that Lie group. And I'm going to remark that this helix dimension is actually very small in practice. It's always smaller than n of g. I think it's always smaller than 1/3, or always at most 1/3 times n of g. And when g is simple, this is either 0 or 1. You can do it by a brute force, for example, classification of simple Lie groups. So the fundamental, this comes from the fact that the fundamental group of certain familiar groups are like at most Z. So it's not very bad. I mean, this theorem still is correct in the order of magnitude, for example. Yeah. Okay, so this is very abstract, and you can forget about it at this point. And I think in the next half of the talk, I'm going to explain what we did if we want to prove this conjecture for SL2 of R, and all the steps are going to be quite general. So hopefully you will understand at least intuitively how the whole proof goes? Okay.
Just so that while we listen to this, is SL2 tilde the sort of, is that got all the difficult features you think to handle the general case? I mean, you're going to explain to SL2R and that'll be your general theorem basically. So, I mean, suppose somebody wanted to understand the missing case. That's really a critical case?
We don't think it is. we took some effort into it, and we were not able to prove it using existing like methods. So
okay, maybe I'll return to it at the end of the talk. Okay.
Yeah, I think one new idea, at least one new idea is needed to deal with that. But yeah, let's first look at SL2 of R, and maybe in the end we can look at the universal covering a little bit. So I'll from this point on, I'll start talking about what are the ideas in our proof of the SL2 of R case. And the first one is actually basically what we already covered, namely the sharpness of the exponent. So the sharp exponent is 1/2, and we had the torus example showing it's sharp. And actually, you can generalize this to a similar construction showing that 1/ng would be sharp for general G if you can actually prove that. So,
sorry, I'm going to disturb you again.
Yeah.
For solvable or nilpotent, these things are understood, and
yes,
how does your conjecture fit? Can you maybe you can explain your?
Yeah, I'm going to show.
You'll get to that. Okay.
In a few slides. So yeah, so actually in this slide you will see that if G is unimodular and solvable, this is proved by McCruden.
Okay, all right. So sorry.
Covered a little bit later, but yeah, we will get into that. But before that, I had one more slide showing that what will we know about SL2 of R? What are some good things? So this slide shows the Iwasawa decomposition that are often used by people who study SL2 of R. So if G is SL2 of R, you can decompose it as the product of KAN, and this multiplication is a diffeomorphism. So what are those groups? So the group K is the maximal compact group. It's going to be SO2 of R. It's isomorphic to the torus as we just seen. And this group AN, I put them together and I call it B. Sometimes it's called the Borel subgroup. And it's isomorphic to the group of AX plus B, as we saw in my introduction. B is going to be solvable. And B is homeomorphic to R2 topologically. And one difficulty is that B is not unimodular. So probably we need, so you know that B is homeomorphic to R2. So probably we want to use some good properties about B to establish this Brunn-Minkowski in SL2 of R. After all, the bad example comes from K, and B is homeomorphic to R2, and 1/2 is the magical exponent we're after. So we're going to analyze B in a minute. But sticking with G for the moment, and you have, so B is not unimodular, and we have to talk about the left and right higher measures if we want. So let D of mu B to be a left higher measure on B, and D of nu B to be a right higher measure. And then under suitable normalizations, there's an integral formula corresponding to the decomposition G equals to K times B, where you have very nice equality. D mu of G is equal to D mu of K times D nu of B. So almost like Fubini, but G is not a product between K and B. It's just a product set, but it's not a product group. And G is simple, so you cannot. I mean, there's no exact sequences of Lie groups, as we'll be seeing. If you have exact sequences, it will be in a much better shape. So this is the basics. These are the basics of SL2 of R. And as before, when we were doing the proof, we first started to look at B and asking if you have good properties from this B. So let's look at B in a closer way. Okay, so as I put in the title, we want some Brunn-Minkowski or Brunn-Minkowski type inequality for B. And actually, if B were unimodular, then this would be very nice because there's a theorem by McCrudden in 1969 saying that if you have a unimodular and solvable Lie group, then the sharp Brunn-Minkowski is 1 over n of G. So he already has our conjecture in this case. And later, so this theorem was very useful, especially useful in the nilpotent case. And later, special cases were rediscovered by Gromov, Khrushchevsky, Leonardi, and Mansell and Tao. So because
in this case, he's defining n of G the way you defined it.
I don't think no.
The point is, yeah, he doesn't talk about the maximal comp. Yeah,
he has some exact sequences, and he defined n of G using exact sequences.
Yeah, because the reason I ask is because then it's not obvious from his point of view what the general case should read. Yeah.
Yeah, probably. I have no way of knowing that, but yeah, he didn't have this formula. He didn't have this formulation. Okay, so but our case is we're facing a non-unimodular group, and this can cause a lot of pain. For example, if you just look at the left Haar measure, then the left Haar measure of xy is bigger than mu b, the left Haar measure of y, but can be much smaller than that of x. And as a consequence, you cannot hope to have the same inequality for the left measure only for any alpha bigger than 0. And this is completely general. So for any non-unimodular group, you cannot hope for a Brunn-Minkowski only involving the left Haar measure for any positive alpha. So this is just impossible. You can have it for alpha equals to infinity. I should put, you cannot hope to have it for alpha less than infinity. But the trivial one isn't very useful. And we were thinking about the following question: how to formulate an analog of Brunn-Minkowski on B with sharp exponent 1/2. How can you get this 1/2? How can you ask a question that involves 1/2? And at this point, we were actually inspired by some work done by Kemperman, as shown in the next slide. Okay, so a little bit off the topic. Here's a theorem that's not Brunn-Minkowski, but looks very relevant. So this is a theorem proved by Kemperman in 1964. So the first part is very beautiful, and I think it's better known, that if you have a connected unimodular non-compact group, then you always have mu of xy bigger than mu of x plus mu of y. But you see our Brunn-Minkowski has an exponent, but he wasn't interested in the exponent for that point, for that moment. But a more important thing is that he has his second part. He proved that for a connected and non-compact group G, if you have mu and nu to be the left and right Haar measure, then you have this very beautiful inequality, nu of x over nu of xy plus mu of y over mu of xy less than 1. So very fortunately, he had this form of inequality, and when we read his work, we were inspired by this inequality to have a conjecture that's true, that has the 1/2, and that's about the Borel B. So we'll show it in the next slide. So this is our conjecture for general groups. It doesn't have to be unimodular. So if G is a locally compact group, and then you have this inequality, you see we simply put 1 over ng around the two summons, and it happens to be correct, for example, in SL2 or in B. So very fortunate for us in this case. And we also conjecture the exponent 1 over ng is sharp. And actually, our result is about this more general conjecture. So we show that the exponent, if it's correct, is always sharp. We also show that the conjecture can be reduced to simple Lie groups. And we also show that the conjecture is true if we replace 1 over ng by 1 over ng minus hg. So ng and hg doesn't have to do with whether they are unimodular. So certainly a nice thing for us. But the important thing is that we are able to formulate this conjecture that is true in a lot of cases. And actually, as you can see, the best thing is that this conjecture helps us even if we wanted to deal with the previous conjecture. So seems to be irrelevant, but has to kick in at this point. Okay, so we recall this conjecture, and we did something for B in our paper, which is the theorem in the middle. So for a non-unimodular group, we actually proved that if the conjecture holds for the kernel of the modular function, then it holds for the whole group. So maybe let me recall for 1 minute what the modular function is. So the modular function characterizes how, so your group is non-unimodular. So one way to say it would be how much does left hard measure differ from a right hard measure in different points. So that would be one way to say it. And then it's a function, it's a homomorphism from G to R. So its kernel has to be the entire group, or actually part of it. But on that kernel, it's going to be unimodular. So we already know good property about the kernel by Macruden's result. So as actually a corollary, we know that our conjecture holds for all solvable Lie groups, and in particular for the B in SL2 of R. Okay, so now it's probably the most the most challenging part for me to explain a little bit about our proof of this reduction, because I think it's explainable and it's worth it. Okay, so maybe let's forget about our theorem in the middle for the moment, and because our proof of the theorem was inspired by the proof of Macruden's proof, where he used a proof of Macruden's theorem and the theorem he used to prove his result. So let's look at the theorem on the bottom, which is Macruden's theorem, and I'm going to explain how he proved his theorem in most cases, and then explain how that inspired us to prove our reduction. So we also needed his theorem, so it's good to recall his proof in any case. So his theorem says, if you have an exact sequence of unimodular locally compact groups, 1 to H to G to G quotient H and then to 1, he probably didn't put it this way, but that's what essentially he proved. And assuming H and G quotient H have the Brunn-Minkowski exponent 1 over N1 and 1 over N2 respectively. I didn't define Brunn-Minkowski exponents, but that's the exponent you put on the inequality where it's correct. Then you know that G has the Brunn-Minkowski exponent at most 1 over N1 plus N2. So this is like, so in particular, this theorem tells us how to pass from the Brunn-Minkowski in R to R squared and to R to the B. So this is a very nice theorem. You can recover the proof of Brunn-Minkowski once you know this theorem. So I'm going to, I would like to talk a little bit more about this theorem. Okay, so the theorem is, again, rewritten here. And this slide is going to highlight that we understand his proof as a spillover argument. So I'm going to show you a picture that hopefully explains what a spillover argument is. Okay, so it's going to be on the next slide. Okay, so assuming we're trying to prove the Brunn-Minkowski for x plus y in R2, so look at the third line. You have two sets x and y, and we want to know, we want to have a lower bound of x, the measure of x plus y in R2. So how are we going to do this? Well, we can look at, so R2 is a product of two R's. We will the horizontal R as the base, and we will the vertical R as the direction of fibers. And we can decompose our X and Y into different sets. We can look at subsets of X and Y, for example, our X1 and Y1 and X2 and Y2, such that each subset has the same fiber length, or roughly the same fiber length in practice. So this is a very clean example. And then you can look at, say, the sum of X1 plus Y1. You see on the first line, there's a sum of X1 plus Y1. And the right-hand side, you have the sum set. The sum set has a narrower base and taller fibers. And on the other hand, if you look at the sum of X2 plus Y2, then it has a like larger base, but shorter fibers. So how can you get a lower bound of the volume of X plus Y? Well, you can get a lower bound by simply looking at the union of X1 plus Y1 and X2 plus Y2. So these two sets might have the same measure or similar measures, but you know that when you take the union, they cannot overlap because the first set has taller fibers. So you just keep track of how much spillover of the first set is over the second set, and then you just add things up. And if you it turns out that if you take the subsets cleverly, and of course you need to take more than 2 subsets, you take many subsets, and if you take it cleverly, you just use this argument and can prove the Brunn-Minkowski in R2 from the Brunn-Minkowski in R. So this is one thing I found very interesting, and I wanted to explain this. So this is McCruden's spillover argument. And it's also helpful when we were trying to prove our non-unimodular version of the Brunn-Minkowski on B. So back to our conjecture, we have this conjecture, and we have this theorem. So the theorem says if you prove this conjecture for the kernel of the modular function, then it holds for the whole group. And this proof takes a few pages, but I think the most important idea is to use the spillover argument. And one more observation that actually says you can chop x and y into pieces such that on each piece the modular function is roughly a constant. And well, I mean, it will be too difficult to state the whole proof, but this is one crucial ingredient at some point in our proof. But yeah, I mean, on B, we were able to chop it up, but you might wonder, for example, on other groups where the modular function is discrete, this might be inefficient, but turns out that we don't need to worry about the other case that much. But yeah, maybe I'll talk about this technical point in the end, but I'm just saying that using this, we can prove the Brunn-Minkowski in B in the form of our conjecture in the first line. Okay, so this is what we have for B. And I have only one more crucial ingredient to explain. Okay, so we still want to prove the whole conjecture for SL2 of R rather than just for B. So B is very nice, but it's solvable, and we don't want our theorem just for solvable groups. So we recall our integral formula that looks very beautiful. D mu G is equal to D mu K D mu B, and try to use that. And we also recall what we proved on B. So we were able to prove on B a Brunn-Minkowski inequality that's shown in the third item on this slide. So here's the crucial thing, how to pass from B to G. And then here we use the random fiber trick, which was inspired by the work of my other two collaborators, Ifan and Min. So they were looking at Kemperman's inequality, and they did some very nice thing about that inequality. But the trick of their work is that you often, when you're looking at some sets, you often just look at fibers, and then you look at fibers randomly to capture the properties of whole sets. So in particular, what's our approach here? If you have X and Y in the whole group G equals to SL2, then you can consider fibers. So, I mean, I couldn't call them fibers because you don't have exact sequences, but what we're considering is little k1x intersecting with B and y little k2 intersecting with B. So those are like right fibers and left fibers of B, but you consider those sets, and you can use the Brunn-Minkowski on B to get lower bounds of their products, which are meaningful objects to investigate, so mu of B and nu of B. And then the final step to close it off would be actually we design a probability measure that depends on X and Y, and then say that, okay, you choose K1 and K2 randomly with respect to these two measures, and then use the lower bound in the first step and use the integral formula. Then you have the conjecture for G. So this is by a computation and maybe, and of course, Holder's inequalities, but it's, I think this is a conceptual reason, and the computation very fortunately works. So that's the final step, how you pass from B to the whole SL2 of R. And so basically, that's the sketch of the proof in the SL2 case.
Can you maybe say a little, one more, maybe 30 seconds more about how you make this this design probability measure?
Actually, the measure is very simply constructed. It's going to be proportional to the length of the fibers. So if you look at our original paper in the abstract, we say that this is a proportionated averaging trick. But the motivation, I mean, probably we need more motivation for that. Like our motivation is that in a lot of proofs of Brunn-Minkowski, it's very nice to chop the sets into subsets of equal volume. So we initially did that, and then at some point we realized that how we construct this probability measure proportional to the average, to the length of the fiber. So if you want to be more specific, but this is like, I mean, this is not very involved, not very secret, but it's important to discover this way to construct the measure. It's very straightforward from X and Y. Yeah. Okay, so maybe a little bit more about the universal covering. So for the universal covering of SL2 of R, we conjecture the sharp exponent to be 1/3. This might well be wrong, but I personally believe it's still correct. But as you can see that the previous method, you're averaging over K, for some reason, for the reason of this method, it doesn't see the expansion on K. So it only gives you what you got on B. And for the universal covering of SL2 of R, unfortunately, K is not going to be compact. It's going to be R. So you don't have this full 1/3. And this is completely general. This is the reason why we only get 1/n minus H. Okay, so in the end, I have a few more remarks. Some of them are very technical, so feel free to skip some of those. So I just want to say what happens for general topological groups. Why automatically Lie groups play a decisive role. So the first is that we have Gleason and Yamabe, and we can reduce the conjecture to Lie groups and use the Levy decomposition, Iwasawa decomposition to reduce it to simple Lie groups like SL2 of R. So that's how the reduction looks. And in our paper, we also proved that N and H, those are well defined. Those might be of independent interest. And actually, when reducing the non-unimodular case to the unimodular case, we had a little more technicality. We actually proved that either you have an exact sequence between them and R, or the kernel is an open subgroup where everything is very nice, because open subgroups, you can just replace the whole thing by it. But you need to do a little extra work in the non-unimodular setting when you have an open subgroup, but that's doable, similar to the previous considerations. And the final thing is that, okay, so this might be a very technical point, but it's very interesting why this reduction works, why this reduction gives you the correct exponent, why does it match the exponents? So this looks like a miracle, but I can only say that it's because you have nice additive properties of the dimension of the maximal compact groups when you have certain exact sequences. Yeah, like for example, when the groups are connected, you automatically have the dimension of the maximal compact groups in the middle to be equal to the sum of the two dimensions of maximal compacts in the two sides. So this is, in some sense, helps us to get the sharp result in our conjecture. I mean, this is very technical. This has to do with the induction, but I can talk about more if you're interested. But I think that's all I wanted to say today. Thank you so much for the attention.
Thank you. Questions? Okay, so go ahead, please, Tom.
Oh yeah, no, I have some questions about cases of equality. You showed us some cases of equality in Rn. Do you know what they are for the group?
Okay, so that's a very interesting question. Like I don't think it's clear even for solvable groups. I'm not sure. Like in general, it's like more complicated. One thing we are sure is that this alpha is going to be sharp, but this doesn't stop you from asking the question. If you're asking the original question, for example, this question, even on the bottom, given mu of x and mu of y, how small can mu of x?
Yes. Yeah.
So, but in this question, if you think about it, you have to fix a mu to ask this question. If mu is allowed to, you're allowed to rescale mu, then our theorem is sharp. But I mean, if you fix a mu, then like mu of xy to the 1 over d might not be possibly equal to mu of x to the 1 over d plus mu of y to the 1 over d. And I think that's another very interesting question to study, but also like qualitatively a little bit different from what we're studying here. So
Yeah.
if you mu, then this becomes very interesting. And yeah, there are references saying asking this, but yeah, I don't think it's generally understood. We certainly did a direction.
Yeah, well, what I meant was you were showing us originally where you had these parallelograms, and then you actually had equality, right?
Yeah, right.
And I guess if I do that for disks, I don't get the same thing.
Yeah, I don't think you get the same thing in, yeah, if you do it.
And another general question, are you familiar with Braskamp-Lieb?
A little bit. Yeah, I use it in my research.
Ah, okay.
His thesis has that in its title.
Ah, okay.
I understand some perspective a little bit.
Yes. Now, is there that's closely related to Brunn-Minkowski. So, is there an analog for these non-abelian cases?
Yeah, that's another interesting question. So there are other ways to ask this in non-commutative setting, I suppose. For example, there's a paper that asks about the set of midpoints on Riemann manifolds. I think that's another way of asking it. And I think that paper has some Braskamp-Lieb context, but I don't know. So yeah, if anyone knows that, that would be very nice. I don't know very well. I will look into that. Yeah.
Yeah, because I think, at least in the convex, in the case where you take your sets to be convex, Braskamp-Lieb implies it for RD, right? This gives you, it's a more general, there's even something more general than Braskamp-Lieb, which is sometimes referred to as Witten-Helfer-Scherström, which is an identity, actually. It's a more complicated expression.
Yeah, actually, I'm not familiar with this connection. So yeah, maybe we can talk more. Like
sure.
On this. Sounds very interesting. Yeah.
So I won't bother you with the SL2 tilde. That'll bother you privately. But as you talk, I have a question. I think Minkowski was probably interested in this because of the geometry of numbers.
Yeah.
And because he was trying to improve his first and second theorem in the geometry of numbers for lattices in Rn. But now we have lattices in semi-simple groups. So I wonder if you ask questions about sort of tessellating the Lie group, you've got a discrete subgroup with maybe some cofinite volume, whether your new inequality, which you have proved in the linear case, might be useful in terms of tessellation questions in SL2R, just like, in other words, thinking of why Minkowski might have looked at this, he would take a convex set and see how it covers the space. So have you thought of that? Just seems natural, given that you have, it seems like you have the first Brunn-Minkowski for SLNR, as you point out.
Yeah, that's another very interesting direction.
So the point is to bring back Minkowski through a discrete subgroup. That's all I'm saying.
Right. Yeah.
I mean, questions of volumes of the quotients are well studied, and there are many experts at that. But the question of maybe not the volumes, but covering with arbitrary sets, which sort of not tile or cover the space by translations, might have maybe your inequality can improve those kind of. There's a lot of study of that, I'm sure. Anyway, I'm just pointing that out.
Yeah, I would like to understand more about Minkowski's motivation, but a lot of his references were in German. I don't understand it that well. So.
That is not an excuse.
Yeah. Maybe I'll talk to you more privately to know like a good way to look at it. Yeah.
Anyway, beautiful. Yeah.
Yes.
Other questions? Well, it does not seem to be the case. So let us thank our speaker again